Welcome! In this lesson, we explore green chemistry through quantum mechanical modeling of green catalytic cycles. We will connect chemistry, mathematics, statistics, and visuals into one clear story. A catalytic cycle shows how a catalyst helps transform a substrate into a product while the catalyst is regenerated. We start at the top with substrate plus catalyst. The cycle advances to the first intermediate, then to the second intermediate, finally to product plus catalyst, closing the loop. This closed loop is key to green chemistry. Fewer steps, less waste, and lower energy. Quantum mechanics lets us compute reaction energies and barriers. We solve the time-independent Schrödinger equation. The Hamiltonian acts on the wave function equals energy times the wave function. The wave function describes the electrons. Using the Born-Oppenheimer approximation, we fix the nuclei and solve for electronic energies to map a potential energy surface. Here is a potential energy profile along a reaction coordinate. The red curve is the uncatalyzed path with a higher barrier. The green curve is a catalyzed route with a lower barrier. The activation energies are shown as double arrows. A lower barrier increases the rate exponentially by the Arrhenius equation. The rate constant equals a times the exponential of negative EA over RT. The ratio of catalyzed to uncatalyzed rates involves the difference in barriers. Even a 20 kilojoule per mole drop can boost rates by about 1,000 at room temperature. To connect energies to rates and selectivity, we use a microkinetic model. We write elementary steps with forward and reverse rate constants. Then ordinary differential equations describe the intermediate concentrations. The product formation rate follows from the last step. Quantum predictions carry uncertainty from methods and conditions. A histogram of computed activation barriers shows the spread across conformations and solvents. We summarize with a mean and a standard deviation to inform risk and safety margins. Descriptors can correlate with barriers, enabling faster screening of green catalysts. Here, a binding energy descriptor correlates negatively with the barrier, with a correlation coefficient near minus 0.85. Putting it together, the workflow for green catalytic design is define a molecular model for a green catalyst, run quantum calculations, and solve the Schrödinger equation, construct the potential energy surface, simulate the kinetics to predict rates and selectivity, and evaluate green metrics like energy, E-factor, and yield. In summary, quantum mechanics quantifies energies and barriers, microkinetics turns them into rates, and statistics communicates uncertainty. Together, they enable cleaner, safer, and more efficient green catalytic cycles.